All right. So in this final video, I wanted to just spend a little bit of time reviewing. I wanted to just kind of review all the different statistical tests that we've encountered in this class. I think really I like to do this video because it's a nice kind of end piece to showing you all of the different tests that we can do, why we want to do them, and just a kind of refresher on the way that we set up these particular tests. So the very first kind of inferential test that we really started looking at was the one sample Z test. The one sample Z test uses the Z table that allows us to find percentages in particular Z score values. And we specifically use the one sample Z test when we are testing hypotheses concerning the mean value in a single population with a known population variance. So if we have a population parameter in the question, if we have a parameter in the question, then we typically are going to be looking at running a Z statistic or a Z test, specifically when we have a population standard deviation. So in order to obtain our Z statistic, we take the mean that is given in our question, subtract from that the population mean given, and divide by the standard error. The standard error being the standard deviation of the population divided by the square root of n. Here we are looking at our normal distribution, where again, 50% is to the left, 50% is to the right. We obtain our critical Z value based on whatever the alpha is, and we determine whether the Z value that we obtain falls within that rejection region. Now, one sample Z-tests are great when you have all of that information, specifically about population parameters. But in reality, we oftentimes do not. And this is when we move into the one sample T-test. This is when we want to compare a mean value that we have from a given sample. And remember that samples are subsets of the population. And we want to compare that mean value to a known value in the population. So when you're reading the kinds of statistical questions, what you want to ask is, we have some value that is taken from a sample, and do we want to compare it to a population mean or to a known value? So we take the difference from the mean that we collect. Now, again, this is coming from the sample and the population mean or the known value that's given to us, and we divide by the estimated standard error. Now, what makes the estimated standard error estimated is that instead of the population standard deviation, we are going to use the sample standard deviation. So in our one sample T statistic, we are going to have a mean and a standard deviation from that sample, as well as an N value. And we're going to incorporate those values in our test statistic. This is going to include the use of the T table, which again, we saw is similar to the normal distribution table, but it is dependent on our degrees of freedom. Now remember that as the degrees of freedom goes up, our sample size goes up, and our T distribution more closely approximates a normal distribution. So our T statistic here is the mean from our sample, so our sample mean, so the sample mean, minus mu, and mu can be either the population mean value that we're comparing to or a known value, and we divide by the estimated standard error. So this is the estimated standard error, which we define as such. The standard deviation, again, from the sample divided by the square root of n, and this being our sample size. So again, here we've defined each of these particular terms that are found within this calculation. Now, a little bit of comparison between a Z-test and a T-test. I like this table just because it kind of lays out side by side a really nice comparison. So we are obtaining a Z statistic and we're obtaining a p-value in a Z-test, whereas in a T-test, we're obtaining the T statistic. We use the normal distribution. This is the Z table in a Z-test, while we use the T distribution or the T table in a T-test. The denominator for our test statistic, which generally speaking, we always want to be small so that our test statistic would be large, is the standard error, while the t-statistic utilizes the estimated standard error. So again, the standard error for the z is just the population standard deviation over the square root of n. Estimated is the sample standard deviation over the square root of n. For a z-statistic, we do know the population variance, but in the t-statistic, we do not. So this is why we use the sample variance in order to estimate that population variance. Are degrees of freedom required for this test? And in a z-statistic, no, because the population variance is known, so we're not having to make any kind of inferences about that population variance. But in a t-statistic, degrees of freedom are indeed required. So the degrees of freedom for the t-test is equal to the degrees of freedom for sample variance. This is just n minus 1. Now, what does the test actually measure? These are measuring the same thing, the probability of obtaining a measured sample outcome, right? What's the probability of obtaining this particular value? Is it in this alpha region or is it not in the rejection region? And we can infer whether or not the null hypothesis should be retained or rejected. So moving into more t-tests, we have the independent samples t-tests. This is when we have different participants in each of our two groups. So remember that t-tests are going to be where we are having two groups. And in an independent samples t-test, we have two groups of different participants. So we are wanting to compare the mean difference between our two groups. So let's say condition 1 and condition 2. We have a mean for group 1 and a mean for group 2. We are ultimately wanting to compare these mean values. We also use the independent samples t-test when we have an unknown population variance in one or both populations. Now, ultimately, in a lot of our statistics, we want large test statistics. Larger test statistics are going to be found further out in those distributions. This just means that it is less likely that a sample mean would be likely to occur if the null were indeed true. Because if the null is true, usually centered at 0, right? Remember, the height of this distribution means the more frequent these particular scores are being found. And centered is at about 0. As we go out to the sides, the frequency of these more extreme scores are less and less. So larger test statistics take us further and further out to the side. Now, our test statistic is the difference between the two sample means that we have. Again, this is coming from the information that we find, and the mean difference in the null. Now, again, the mean difference in the null hypothesis. So the mean difference in the null hypothesis is oftentimes 0. So usually in the test statistic, we just write mean 1 minus mean 2. And we divide that by the estimated standard error. Now, again, the estimated standard error is this pooled sample variance over n1 plus the pooled sample variance over n2, taking the square root of that. Our degrees of freedom for an independent samples t-test is n1 minus 1 plus n2 minus 1. Or we can just write capital N, which is the total sample size, minus 2. And when we say minus 2, this is taking into account that there is n minus 1 degrees of freedom for each group. Here are the formulas that we saw before. Now, in order to solve for our pooled sample variance, this is going to depend on whether we have unequal sample sizes or whether we have equal sample sizes. So if we have unequal sample sizes, then we have to essentially create a weighted average of the sample variances. So this is the variance of group 1 times the degrees of freedom of group 1 plus the variance of group 2 times the degrees of freedom of group 2 over our total degrees of freedom for unequal sample sizes. With equal sample sizes, we simply just take the average variance. Once we have the pooled sample variance, we are then going to add that into our estimated standard error formula, taking the square root of the pooled sample variance over n1 plus the pooled sample variance over n2, and then our obtained test statistic, which again, we will then compare to our critical t-value that is found by looking at our alpha region or looking at our alpha value, and we'll determine whether our t obtained is in the rejection region. So mean 1 minus mean 2, these are coming from our samples. Mu1 minus mu2, the null hypothesis for an independent samples t-test is often 0 because, again, our null hypothesis is just that these two are equal to each other. So if they're equal, then this difference would be 0. And we divide by the estimated standard error of the difference. The second type of t-test that we looked at was the related samples t-test, also known as the dependent samples t-test or the paired samples t-test. This is when we use the same participants in each particular group. We do not have two independent groups, but what we're doing is calculating difference scores to see how individuals have changed from condition 1 to condition 2, or from time point 1 to time point 2. So our test statistic is just that mean difference, or the mean of the difference values, minus the mean difference stated in the null. Now, the mean difference stated in the null is always 0. So we have our mean difference in the numerator divided by the estimated standard error, or the standard error for the difference scores. Now, this should look familiar to you because this setup is basically what a one sample t-test looks like. So our degrees of freedom for a related samples t-test is the number of difference scores that we have minus 1. So remember, condition 1 and condition 2, paired samples t-test, each individual is giving a value in each of the conditions. And then what we have is a column of difference values. And it's from this column of difference values that we're actually going to be doing all of our analyses. So some calculations for the paired samples t-test. We have the variance of our difference values, which is just the sum of squares, divided by the number of difference values minus 1. We can write our sums of squares formula using the computational formula. And the computational formula says that we're going to add up all the squared difference values, subtract from that the sum of the difference values squared divided by the number of difference values. And again, D here just stands for the fact that we're looking at that single column of difference scores. Once we have our variance of the difference scores and our number of difference scores, we can do our estimated standard error, standard deviation of those difference values, which will always be a positive number because standard deviation is measuring dispersion, divided by the number of difference values. And our obtained t-statistic is just the mean of our difference values. This is from our sample. The mu of the difference values, this is always according to our null set to be 0. And then divide by our standard error. We want to determine whether our t-statistic falls in the shaded region compared to our critical t-statistic. If it is, then we can reject our null hypothesis. Now, moving away from t-tests, we started going into ANOVA designs. And the first ANOVA design that we covered was the one-way between subjects ANOVA. Remember that the 1 in the one-way ANOVA just means that we're looking at one particular factor. And what makes an ANOVA separate from a t-test is that in that factor, we have 3 or more levels. So ANOVA just stands for analysis of variance. Remember that we're looking at the variances between our groups and within our groups and making a ratio of this variability. In our ANOVA designs, we talked about K. K is just the number of groups that we have within our factor, often 3 or more. Our degrees of freedom for the between groups component is K minus 1, so the number of groups minus 1. The degrees of freedom for error is our total sample size minus the number of groups. And our degrees of freedom total is our total sample size minus 1. Remember that ultimately we are going to be getting an F ratio, which is the variance between our groups divided by the variance within our groups. Ultimately, we want the variance between our groups to be large, and we want the variance within our groups to be small. The variance between groups just refers to the fact that we're looking at the differences between our means between the various conditions. We want these values to be pretty different from each other, which would mean the variance between groups is larger. And we want the values that are contributing to each of those means, so the within group components, to be relatively small. So At the end of the day, we're looking at variances in a ANOVA or in an ANOVA design. And variance is just the sum of squares divided by our degrees of freedom. And we can look at this and organize it really nicely in our summary tables. Ultimately, we are wanting to know, is our obtained F statistic, which is just the variance between groups over the variance within groups or error, greater than the one found in our F table? And remember that our F table is positively skewed because, again, when we're looking at variability and variance, we can't have any negatives. And we're going to use the F table that is corresponding with our specific alpha value of interest. So we start by partitioning our sums of squares and our degrees of freedom. So we have a sums of squares total, and we partition that into a between sums of squares and a within sums of squares. The degrees of freedom total is broken down into a degrees of freedom between and within. And remember that the between and the within must add together to give you back the total. So it is a nice way to always just check that you are doing your calculations correctly. Each variance in the F ratio is computed as the sums of squares over degrees of freedom. And what you'll notice is you have a sums of squares between and a degrees of freedom between, which would give you the variance between. Then we have a sums of squares within and a degrees of freedom within, which would give you the variance within. Once we have these two variance components, then we can just simply make a ratio, which will give us our F statistic. This is the F ratio, the variance between our treatment groups divided by the variance within our treatment groups. So a summary of calculations that we saw and that we used with our ANOVA designs are sums of squares total, SST. This is the sum of x squared, which is all the x values, summing all those squared values, minus the sum of x's squared over n. Remember that sums of squares will always be positive. Our sums of squares between groups, we have this nice little formula here, sum outside the bracket, sum of x sub k squared over n sub k, minus sum of x's squared over n. Remember that if your k is 3, you're going to have 3 components here. If your k is 4, you would have 4 components within that bracket that you would have to add up together. And then once you have 2 of these, sums of squares total between or within, you're able to get the third one just by subtraction. One thing that I recommend is just taking the total and subtracting the between, and you'll get your sums of squares within. As a reminder, so here's our sums of squares formulas. Here's our degrees of freedom formulas, k minus 1, number of groups minus 1. Degrees of freedom for error, which is just n minus k, our total sample minus the number of groups, and our degrees of freedom total, which is just capital N minus 1, the total sample size minus 1. We next moved into the within subjects ANOVA, also known as a repeated measures ANOVA. So we see our degrees of freedom between groups is still k minus 1, so the number of groups minus 1. Now we have that between persons component that is found within the repeated measures ANOVA. And it's thanks to this between persons source of variation that we're able to actually decrease our within subject variability to some extent, which makes the within subjects ANOVA more powerful than a one-way ANOVA, generally speaking. So our degrees of freedom for the between persons component is n minus 1, lowercase n. This is just the number in each group, which would be coincidentally the number of people that are in our study. And our degrees of freedom for the error is k minus 1 times n minus 1. So these two components multiply by each other. Now, if we add these 3 components up, you will get the degrees of freedom total. So we need to remember to include our between persons source of variation in any and all calculations, where the same individuals are in each level of the factor. So if we're looking at a group of students that are tested after consuming a sugar pill, a caffeine pill, and an antidepressant, we're getting 3 values from each of the participants. This is when we're having to look at those row means, specifically when we're wanting to subtract out that average deviation. We're still using the F table. We're still getting a single F ratio at the end of the day when it comes to a repeated measures ANOVA, and we're going to compare our obtained F ratio to what our critical F would be based on the given alpha level. So here are some of those calculations again. The sums of squares total is the same exact formula. Sum of x squared minus the sum of x's squared over n. We have our sums of squares between groups, which is just the sum of our sum of x sub k squared over n sub k. Again, this is going to be, you're going to have as many components in this bracket as you have groups, or as you have number of groups or levels, minus sum of x squared over n. For the sums of squares for our between persons or for our subject component, we're taking the number of levels, okay, and we're multiplying that value by the sum of the squared deviations from the row means and the grand average mean. So the reason why we're multiplying it by the specific number of levels is because those are the number of conditions that each person is contributing to. And again, you're the same person in condition 1, condition 2, and condition 3. Now, once we have sums of squares total, sums of squares for the between groups, and sums of squares for between persons, we can just subtract those from the total, and we would get the sums of squares for error, or the sums of squares for our residual. Now, the last ANOVA that we focused on was the two-way ANOVA, also known as the factorial ANOVA. The factorial ANOVA is used when we have more than one factor. And remember that a factor is just another name for an independent variable. So we have factors, and then we have levels, which are going to be the groups that that factor is made up of. So for instance, if drug is our independent variable, drug can be considered the factor, and then there are 3 types of drugs. And those 3 types of drugs would be the 3 levels. So just like when we said a one-way ANOVA had one factor, in a two-way ANOVA, we have 2 factors. So we have factor A and factor B. Now, what makes the two-way ANOVA special is that because we have these 2 factors, we can look at them in isolation, which means that we're looking at main effects. But we can also see whether there is any interaction between those 2 factors. And remember that we can see interactions by whether or not we have intersecting lines within our specific plots. If our lines are parallel, that is evidence for no interaction. We are still using the F table in a two-way ANOVA, but remember that we are going to now have 3 null hypotheses, 3 alternative hypotheses, and we are going to be comparing 3 F ratio values to the critical values found in the F table. We have a null hypothesis for the main effect of A. Remember that main effects collapse across the levels of the other. The main effect of B, and then we have a hypothesis for the interaction between A and B. The degrees of freedom for our first factor A is just the number of levels in A minus 1. The degrees of freedom for factor B is just the number of levels in that factor B minus 1. The degrees of freedom for the interaction is the degrees of freedom of A and B multiplied by one another. Degrees of freedom for error is the number of levels in factor A times the number of levels in factor B multiplied by n minus 1. N is going to be the number of people, animals, subjects, whatever, in each cell. And when we talk about a cell in a two-way ANOVA, if we have factor A with 2 levels, factor B with 2 levels, a cell is just an intersection of the 2. So in this kind of case, we would have a 2x2 ANOVA, and this would have 4 cells. Our degrees of freedom total is just n minus 1. Capital N is the total sample size. Here are our formulas for sums of squares total. This is the same formula that we've seen time and time again. Our sums of squares for A and B are the same formulas that we've seen for the between groups before. But notice here, and I'll highlight this, we are focusing on the sum of x's in the specific levels of that factor collapsed across the other factor. So keep that in mind. The sums of squares for the interaction involves us summing up within the brackets the sum of each cell squared over n sub cell minus sum of x squared over n. but also being sure that we are subtracting the main effect sums of squares out from that. And once we have the sums of squares total, sums of squares of A and B, and the interaction, we can subtract those from the total to give us our error. Now, we also focus in this class on correlations, and correlations have to deal with relationships between specifically two interval/ratio variables. Now, correlation ranges, and we abbreviate this with R, ranges from -1 to +1. It cannot be less than -1, and it cannot be more than 1, okay? Now, the closer your value is to 1 or -1, the stronger your relationship is. The closer your relation or your R value is to 0, the weaker your relationship is. If your value is positive, it is a positive relationship, meaning that changes in X, increases in X are associated with increases in Y. Negative relationships or negative R values are going to be a downward slope where an increase in one is associated with a decrease in the other. And what we can get from correlational designs is what is known as the coefficient of determination. This is known as R squared, where we take our correlation coefficient and square it. And so R squared represents the extent to which changes in one particular factor, oftentimes we think of this as the dependent variable, can be explained by changes in the other. So the way that we write this is the percent variation in Y that can be explained by X. Now, this R squared value ranges from 0 to 1, but we multiply that by 100 to give us that interpretation value. Now, it will not ever be 100%, right? In experimental findings, in research findings, you will never have an R squared that is 100% because we just can't explain everything with just one specific factor or with just one particular variable, right? So this was the computational formula here. Remember that this numerator is the sum of squares for X times Y. This is our covariance. And the covariance is the only portion in this that can be negative. Here we have our sums of squares for X multiplied by our sums of squares for Y. Remember that the sums of squares of X and the sums of squares of Y can only ever be positive. The sums of squares of X times Y is the component that can be negative, okay? Now, our n value in this computational formula just stands for the number of pairs that we have or the number of people. Our degrees of freedom when we're using the Pearson R correlation table is n-2. And we find this critical R value using that given table. Now, again, this is relatively two-sided because we can have negative and positive values, right? So just keep that in mind when you're using this table. Now, what happens if you find a significant correlation? Well, a significant correlation just says that there is a significant relationship between our two variables. Now, can we do something with that? Certainly. We could start to use that to make predictions. And this leads us into linear regression. This is what is known as creating the line of best fit. So for instance, if we're looking at a correlation between X and Y, and we see these scattered dots that give us this kind of pattern, there's going to be one line that has the best formula to run through our data in the best way, right? And we want to figure out what is the equation for that line in the form y equals bx plus a. So this is a little bit throwback to algebra when we're calculating the slope of lines, right? And we're calculating the equation for a line. B just stands for the slope, and A is the y-intercept. The slope just tells us how steep that line is, and the slope can be a negative or a positive number. If your Pearson R correlation coefficient is negative, then your slope will also be negative. If your correlation coefficient is positive, then your slope or your B value will be positive. Your y-intercept is going to be where that line of best fit intersects with the y-axis, meaning when x is 0, that is what your y value will be. Now, we can use this equation to then predict values of y from particular values of x. And so if you place any value of x into your linear regression equation, it is going to pop out a value that is found on that line of best fit, which is then mapped to a specific y value. We can plug those values in we want to explore as x within our given equation. You could also reverse this, right? So bx plus a. You could also say, well, what if I have a value of y, right? Where would that fall, and with what x value would that be related to? So to solve for our slope, we take our sum of x times y, the sum of these products, multiplied by n, minus the sum of x's times the sums of y, divided by n times the sum of x squared minus the sum of x's squared. Remember that b can be negative. That is okay. Because again, if we have a negative relationship, the slope will be negative. The y-intercept, you'll take your mean of the y values and subtract from that the product of b, which is our slope, multiplied by the mean of x. And n in our linear regression formula just stands for the number of pairs or the number of people that we have. And last but not least, we had the chi-square tests. And there were two specific chi-square tests that we looked at. We looked at the goodness of fit test, and we looked at the test for independence. The goodness of fit chi-square test is when we have frequency or count data in two or more groups from a single factor. The test for independence is when we have frequency or count data in two factors. And these two factors must have two or more levels each. Now, what makes the chi-square tests different from all the other tests we've done in this semester is that this is useful with nominal data. Nominal data just, again, refers to groups, right? So for instance, if I have a test for independence and I'm wanting to see if there's a relationship between gender, let's say male and female, and then choice of major at a university. And so let's say we have STEM and non-STEM. I'm not measuring anything continuous. I'm not measuring anything numerical. If you're a male who has a STEM major, you belong into this cell. If you're a female in a non-STEM major, you belong into this cell. So at the end of the day, what we're getting is just counts in values in each of these particular groups. Now, what makes these different is that we are going to essentially assess whether there are relationships between these two in a test for independence. And in a goodness of fit test, we might have something that just looks like this, one factor with two levels. And we're just saying, is there a difference between what we would expect and what we actually observe? And the same rationale goes with the test for independence. Now, in the goodness of fit test, we usually just divide our sample size n by k to get the expected values of what we would think. We could also use already known percentages to say what we would expect in the chi-square goodness of fit test. In the test for independence, we have to calculate our expected values. So remember that in the test for independence, we calculate our expected values as the cell row total observed value times the cell column total observed value and divide that by n. Now, what's super nice is that the test statistic for the goodness of fit test and the test for independence is the same test statistic. So at the end of the day, we're looking at this test statistic right here. So our chi-square test statistic is just the sum. We are summing everything that comes after that sigma notation. We take our frequency of the observed values minus the frequency of the expected values squared, divided by the frequency of expected values. And we're doing this for as many cells as we have. Now, in our obtaining of the chi-square statistic, we need to compare our obtained value to the chi-square table. And the chi-square table relies on degrees of freedoms. So in a goodness of fit test, our degrees of freedom is just k minus 1, so the number of groups or levels minus 1. And in the test for independence, we take the degrees of freedom of that first factor multiplied by the degrees of freedom of the second factor. Now, an important point to make is that chi-square can never be negative. Now, the main reason for this is because of the fact that we are squaring these difference values, right? So if we're squaring a particular value, squaring it means that it can never be negative. Now, ultimately, we want higher and higher chi-square values because that indicates a deviation from what we would normally expect. And remember, at the end of the day, with chi-square, we are wanting to see whether what we have actually observed in our sample is different from what we would expect just by chance or from the expected values that we calculate. And these have been all of the statistical tests that we have done in this semester. And it's important to be able to distinguish between those tests because oftentimes when you are confronted with experimental setups and someone asks you to run specific analyses, it is up to you to determine what is the way that the data is set up, or sorry, what is the way that data are set up within that study? What is the best test that you need to run? And what test is going to give you the best reliable data?